Welcome to my presentation about one-body reduced density matrix functional theory for the canonical ensemble in finite basis set. So this is a project I have done with my supervisor, Klaas Giesberts. So in this paper here of my supervisor and Michael Rugenthaler, they showed a nice overview over one-body RDMFT in the following settings. So they assumed, they worked in the grand canonical ensemble, so in the Fock space. They assumed that they have a finite number of one-particle basis function, and they worked at the elevated temperature. And I wrote here fermionic in brackets because in principle, the paper shows the whole constructions for the fermionic and the bosonic case, but in the bosonic case there is a mistake in it, and I think it for the non-interacting bosonic case it's okay, like we can fix the mistake, but for the interacting bosonic case we don't know yet how to fix it. So just that you're aware of that. And now the question is, what happens for the canonical ensemble? So if we have a fixed number of particles, and if we are in statistical mechanics, we can go from the canonical ensemble to the grand canonical ensemble by the Legendre transform. So we could think to just transform it back, but for the quantum case, this is not possible because the underlying spaces are not the same. So for the canonical ensemble, we work with the n-particle Hilbert space, whereas for the grand canonical ensemble, we work with the Fock space. So we cannot do that, and we need to study the canonical ensemble separately. So now this is just a small introduction to 1-RDMs, but I think you already saw it today, but I just want to make sure that we are all on the same page. So if we have an n-particle wave function psi, then the kernel of the 1-RDM is given by the following expression. So we have the wave function and the complex conjugate of it, and we integrate out n-1 particle, and here we have the normalization constant. And then for a density matrix, which is of the following form, the 1-RDM is given by having the same weights, and then we take the 1-RDM of the wave function that produced the density matrix. And I think, as Julia already mentioned, the nice thing of this object is now that as you see here, the wave function scales with the number of particles, whereas the 1-RDM is independent, or the normalization depends on the number of particles, but not, sorry, that was wrong, but not the number of variables. And that's nice for doing computation for very large molecules or just in general large systems. And then, so this would be the kernel of the 1-RDM, but we can also have the matrix representation of it by taking like the matrix elements of the 1-RDM for a certain density matrix would be the trace of this density matrix, and then we have the creation annihilation operator, whereas the index are the basis we represent our matrix with. So now I want to present the general approach. So if we have non-zero temperature, we have, so of course we have the energy produced by the Hamiltonian, and then we have this term which is, so S is the entropy, and beta is the inverse temperature. And so we have this additional term if we include temperature in our system. And so this functional is called the Helmholtz functional. And our Hamiltonian is of the following form. So we have H0, which is usually the kinetic energy and interaction energy, and this is called this is kept fixed. And then we have our potential. And the minimizer of this functional can be computed by making this functional stationary with respect to the trace zero condition, because of course the density matrix has a fixed trace. And it turns out that our minimizer is of the following form. So we have the exponential of minus beta times the Hamiltonian, and then Z is the normalization constant. And we can now, instead of just like minimizing this whole functional over all like density matrix as it's done here, we can kind of split this minimization, and first minimizing like over all 1 RDMs, and then we minimize over the density matrix which produce this specific 1 RDM. So this is the same. And here we can take out the potential energy, we can take out of the minimization over the density matrix, because we only need the 1 RDM to compute the potential energy. So if we have a fixed 1 RDM and we minimize over all density matrix which produce this 1 RDM, then the potential energy will always be the same. So we can take it out of this minimization here. This functional is called the universal functional because it only contains this H0 Hamiltonian, which is kept fixed, and the entropic term, which is also fixed. So that's why we call it universal functional. And so now the question is this functional differentiable? So if we have a look here at this expression here, then if we take the very simply spoken, everything is differentiable and nice. If we take the derivative, I mean, for the minimizer, like if we have here the minimizer gamma, then of course this derivative should be 0, right? Because we are at the minimum. And then we have here, if we take the derivative, we have here the derivative of the universal functional. And if we see this as v times gamma, then we would have, if we take the derivative here, which would just have v, so we would expect this relation here, that if we take the derivative with respect to the 1 RDM, and here we mean the ground state 1 RDM, we would get minus the potential. So we are interested in this question, but also, of course, this is related to the question for which 1 RDM is there a potential such that the 1 RDM we have here, so the 1 RDM is the ground state 1 RDM. And this is called the v-representability problem. So I give you a 1 RDM, and the question is there a potential such that it's the ground state of such a Hamiltonian together with the entropic term. So these are the questions I want to answer in this talk. So now I want to present the setting. So we assume that we have a finite number of orthonormal single particle states, which we label by just the index I, and NB is the number of this the number of basis functions. And then we can construct the one particle Hilbert space by just taking the C vector space spanned by these states. And from the one particle Hilbert space, we can construct a bosonic Hilbert space by, like, n particle Hilbert space by taking all the symmetric tensor of order n. And the dimension is given by this number here. So this is the number of basis function, n is the number of particles. And then for the fermions, we can do the same thing, but this time we take antisymmetric tensor because our wave functions needs to be antisymmetric. And here the dimension is given by this. And just for simplicity, we require that the number of basis function is strictly larger than n. So of course, we need to have a proper wave function, we need that the number of basis functions is greater or equal than the number of particles. But if we have equality, we have only one choice for the wave function. So this is like the obvious case. So we will not study this, and it's just simpler for notation afterwards. So we exclude the case where these two numbers are the same. So here we already talked about density matrices, and I just call the set of all density matrices by P bar, and plus and minus stands for fermions or bosons. So density matrices are operators from our n-particle Hilbert space to itself. They need to be Hermitian, greater or equal than 0, and they are normalized with trace 1. And so this means if we have the spectral decomposition of a density matrix, that it is of the following form. So whereas these are wave functions from our Hilbert space, and so that the density matrix is greater or equal than 0 means that these weights are greater or equal than 0, and that the trace is 1 means that the weights sum up to 1. And of course, this condition together with this condition means that the weights needs to be smaller or equal than 1. And then we introduce the relevant spaces for the 1-RDM. So we have here, again, for bosons and fermions. So 1-RDM is a Hermitian matrix with dimension of the number of basis functions. And for bosons, the 1-RDM needs to be greater or equal than 0, and it needs to be normalized to n. And for fermions, we have the additional requirement that the 1-RDM squared is smaller or equal than the 1-RDM itself. So this is equivalent to the condition that the 1-RDM is smaller or equal than 1. And this additional condition comes from the fact that our wave function is antisymmetric. And now if we again have a look at the spectral decomposition, and the 1-RDM looks like this. So these Nj are called natural occupation numbers, and the psi-j's are the natural orbitals. And so it means like the condition that the 1-RDM is greater or equal than 0 means that the natural occupation number are greater or equal than 0. This is our normalization constant. And for fermions, we have that our natural occupation number is smaller or equal than 1. So I think in many talks we were, or maybe I go one back. So, sorry. It's easy to check that if we have a density matrix here, we will end up in these sets here. So that's easy to check. But now we had the discussion in many talks about n-representability. So the question is, if I'm now in f element in this set here, is there a density matrix which generates this 1-RDM? So this is the n-representability. And for 1-RDMs, we know the assumptions for our requirements for n-representability. So these sets are all is the full set of n-representable 1-RDMs. And the proof goes as follows. So we assume that we have a 1-RDM in the sets n. And then we write the 1-RDM in this spectral decomposition. And so we can now think of the 1-RDM that it is contained in the simplex with extreme points n times our natural orbitals. So that's for the bosonic case, and for fermions, we require additionally that it is in this unique cube. So here is a picture, or try to illustrate it. So we have 3 basis functions. So each arrow means how many particles we have in each basis function, and we have 2 particles. So this set here, the larger triangle, is our set n bar plus, so for bosons, and the smaller one, this triangle, is the larger triangle restricted to the unique cube, and this is the set n minus, so for fermions. So each 1-RDM of this form can be represented as one point in either the larger triangle or the smaller triangle. And then we can kind of align the extreme points, so these corners, to the density matrix, where we have just all the particles in orbital, like here it would be in orbital 1, in orbital 2, or in orbital 3. And then by linearity, because the map from density matrix to 1-RDM is linear, we find our density matrix, which produces this 1-RDM. So this is proof by Coleman. So now that we know the set of n-representability, we don't need to worry about this anymore. Now, because we are also wondering about this v-representability problem, the question is also what kind of potential do we allow? So our sets of 1-RDMs are contained in this affine space here of Hermitian matrices with trace n. And then to have a finite potential energy, we require the potential to come from the dual space, which in our case, because we are finite dimensional, is if we take the dual of this, it's just the space itself. But of course, we have this additional requirement here. So this implies in the dual that we have a degree of freedom by choosing a constant. So basically, 2 potential are the same if they differ only by a constant. That would be the dual space of this set here. And to, of course, we want to take one representative of this set here, of potential. So we just require the trace of V to be 0, but that's just an arbitrary choice. So we can choose any representative of this set of potential. And this also has a physical meaning, because of course if we have a Hamiltonian, and then if we add a constant to the Hamiltonian, the ground state does not change. So also the ground state 1-RDM does not change. And this is also this degree of freedom, and we just fix the potential by the trace condition. So now we want to study general properties. So first of all, the following theorem, which tells us that the map from Hamiltonian to Gibbs state is invertible up to a constant in the Hamiltonian. So this constant is just what I talked in the last slide about. And the proof goes as follows. So we know that our Gibbs state fulfills the following equation. So if we have a Gibbs state, which is the Gibbs state for two different Hamiltonians, then it needs to fulfill both of these equations. And if we subtract these equations, we are left with these two terms cancelled. We have HV minus HV prime is equal to C minus C prime. So the two Hamiltonians differ by at most a constant. And then it follows directly that the map from potential to the Gibbs state is invertible. And now we have this Nye theorem, which tells us that the map from the potential to the ground state 1-RDM is invertible. So this is a nice theorem because it basically tells us that we only need the 1-RDM to have a full description of our system. Because if I have like a 1-RDM, I can go back to my potential, and then from the potential I can compute, if it's possible, any property that I want. So I don't need the full wave function to describe my system, but only the 1-RDM.
And in which sense this proof is different from Gilbert's or the theorem? You cite, but is it the same as Gilbert's theorem of the existence?
I think maybe because of the entropic term. Yeah.
So this is with that. So it's more general. Because if you set the entropic term to 0, then you arrive at Gilbert's.
Yeah, I mean, I think the proof goes very similar. So I'm not sure if it's more general or just different. I don't know. So the proof goes as follows. So we assume that we have two potential, and they yield different density matrix. So they have different Gibbs state, as we have seen in the theorem before, but that they produce the same 1-RDM. And then we can compute the Helmholtz free energy by just plugging in our density matrix 1. But if we have this expression here, we can add and subtract the potential energy with V2. So here we have the addition, but then of course we need to subtract it. But to subtract it, we don't need the full density matrix row 1, but only the 1-RDM of row 1. So we can just compute it with our 1-RDM. But this expression here is strictly larger than the Helmholtz free energy, but now with Helmholtz function, but now with density matrix row 2, because of course row 2 is our minimizer for our potential V2. And then we arrive at this expression here.
The strict inequality is because the log row is gone, still be gone. Inequality here.
No, it's because our so we have row 1 and row 2, and row 1 is the Gibbs state for potential 1, and row 2 is the Gibbs state for potential V2. But they are not the same. So if we have our potential V1, V2, and we plug in something else than the Gibbs state, we get a higher energy.
Because it's strictly convex, don't you? That's what it said.
Yeah.
If you were not strictly, it could be not injective.
I mean, yeah, the function is, yeah, you're right. Yeah, and then if we change the role of V1 and V2, so we have here V2, V1, and here V2, V1, and we add the two inequalities, then we get the contradiction. So now we want to study a bit more our minimizers, so the Gibbs state. We know that the Gibbs state is given by the following expression here. So now we see, because we have here an exponential, that the eigenvalues of our density matrix cannot be 0. So our Gibbs state lie in the following set. So if you remember, our set for the density matrix was here bar, where we had not the strict inequality, but now we have here a strict inequality for the set where our Gibbs state will be in. And then we can do kind of the same for the 1-RDM. So it turns out that because of this condition here, also our 1-RDM will lie inside our set n plus bar or n minus bar. So we have also for the 1-RDM, we have that the natural occupation number are larger, strictly larger than 0, and for the fermionic case, they're also strictly smaller than 1. And this is, so here again is the picture of, like, we have 3 basis functions and 2 particles. And this is due to the temperature. Because we have temperature, we kind of occupy all possible excited state, at least by a little bit. And this causes like that we go for sure from the boundary to an interior point. So yeah, this is a property of including temperature. And then, as mentioned at the beginning, physically relevant are the v-representable 1-RDMs. So all the 1-RDMs which are produced by a potential. So there is a potential such that this is the ground state 1-RDM. And now we already know that this set is for sure a subset of this set here. Because the 1-RDM of the Gibbs state will lie inside here, and of course this is the set of all possible Gibbs state. But we don't know yet if these sets are the same. So we just know that it's a subset. So now I want to study a bit more the universal functional f, because at the end of the day we want to show differentiability of this functional here, of the functional f. So the fifth theorem is that the universal functional is convex, and the proof is not so hard. So we make a convex combination of 2 1-RDMs, and then as you mentioned before, the Helmholtz functional is strictly convex. This is due to the fact that, so the Hamiltonian is linear, but the entropic term is makes the strict convexity. And then if we compute this expression here, so we just use the definition of our universal functional, where first we have an infimum over density matrix, which produces the first 1-RDM, and then we have an infimum over density matrix, which produces the second 1-RDM. And here, like in this step, we use the strict convexity of our Helmholtz functional to get this expression here. Maybe I should mention we do not get here, I think, strict inequality because of the infimum. So, I mean, in principle, if we don't have here this infimum, we would get a strict inequality. But because of the infimum, we only get this inequality here. And then this is the same as I made here a mistake, I'm sorry. The Helmholtz function with 0 potential, where we have the infimum over density matrix, which produces our 1-RDM lambda, and this is by definition our universal functional at the 1-RDM gamma lambda. Yeah. So now we know that our functional is convex, and convex function have some nice property. And one of the nice things or concept that we have for a convex function is the concept of subgradient and subdifferential. So we assume that we have a finite dimensional vector space and a convex function. And then we call an element of our vector space the subgradient of our function at the point x in the domain of our function if the following inequality is satisfied for all other points in the domain of f. So this is just the inner product. And so the set of all of these elements which satisfies the inequality is called the subdifferential, and one element of this set is called a subgradient of the function f at point x. So this is an illustration of it. So we have here a convex function, and then as it's already mentioned in the name, it's kind of a generalization of differentiability, because what this means is that we have kind of tangent lines which are aligned at this point here, so f of x, and the inequality means that the tangent line is fully below the function, like our convex function. So the nice thing about convex function is that usually differentiability is a kind of a local property, so we only know that some locality. But for a convex function, we get like a global information. So we got the global information that the tangent line is below the convex function. And now if we assume that we have an element of the subdifferential, so minus v, of our universal function at a certain 1 RDM, then, so this is just the definition of it. So this means minus v is a subgradient for our 1 RDM gamma. And then if we collect all the terms depending on gamma on one side, and, here it should be gamma, here both. And if we collect all the terms depending on gamma tilde, on the other side, we get this expression, like this inequality here, and this holds for all gamma tilde. So, and if you remember, we want to minimize this over all gamma. So I have here should also be gamma. So what we get is a candidate for a potential that generates the 1 RDM gamma. And I write here candidate because if we have a subgradient, then we don't have yet that this potential generates the 1 RDM. And the problem is the following, that so this is the definition of our universal functional. And to have v-representability, we need a density matrix behind this 1 RDM. So we additionally need that this infimum here is a minimum, because otherwise we might have here this relation here, but no density matrix behind the 1 RDM. And then we do not have v-representability. And what this means is if we are not able to find here a minimum, that we have here some kind of linear term. So because of course one RDM, the one from the Gibbs state, will have here a minimum, but all the others, like for one point we have here minimum, but here for all the others, because they all have the same subgradient, we will not have a minimum, but only an infimum. So we kind of need two ingredients, that is non-empty subdifferential, and here minimum. Then we have the following theorem, which tells us about the existence of this subgradient. So we have the same assumption as before, a convex function and finite dimensional vector space. And then it tells us that if we are in the interior of the domain of our function, then the subdifferential is non-empty. And if our subdifferential contains only one element, then our function is differentiable, and the subdifferential is the same as the usual differential. Now we have one problem, and that is that our universal function is supported on this set here, which has empty interior in our vector space of Hermitian matrices, because we have the trace n condition. So you see here, if we have two basis function, if we have only one particle, the functional is here, so only supported here or here or here for three particles. But this is not a big problem, because it just means that we can work on this affine space with the trace condition. So we should not be bothered about that. So now I have a small summary, and then we can go to prove differentiability. So we have this relation between potential and 1-RDMs. Then we know that our universal function is convex, that the subgradient exists for all 1-RDM in the interior of the domain of F, and F is differentiable if the subgradient contains only one element. And we also know that minus elements of the subdifferential might generate the corresponding 1-RDM. So now we have what we want to prove in this talk. So we now assume that the minimum in the definition of the universal functional is attained. So for now, we don't need to bother about that. I will later show that this is the case. And then we have that the set of v-representable 1-RDMs, so this set, is the same as the set of 1-RDMs where we have non-zero occupation number, and in the fermionic case, additionally, the occupation number are not equal to 1. And we also that the universal functional is differentiable for all elements in this set here. So here I just have a small reminder of this set here. So first, we know that our functional is finite for elements in these sets here, but these sets are open in our affine space. So we know we are in the interior of the domain of F, so we know that the subgradient exists. But then we know, because we have the relation between potential and 1-RDM, that, so this subgradient is a potential that generates the 1-RDM. Because we assume that the minimum exists, we have v-representability. So we have the first point is shown. Then we know, because we have the relation between potential and 1-RDMs, that there is only one potential that can generate this 1-RDM. So we know also that we have only one element in the subdifferential, which means that we have differentiability of our universal functional. So now we have shown differentiability, and we also characterized the set of v-representable 1-RDMs under this condition here, that the minimum exists. So we still need to show that. And this can be done in the following way. So we have here, so we want to show that this infimum is actually a minimum. And for that, we use the following theorem, that if we have a continuous function over a compact set, the minimum maximum is attained. And we know that the functional is continuous. So this function here is continuous, but we also can show that the set over which we minimize is compact, and therefore we can use this theorem to show that the minimum in the universal functional is achieved for both the fermions and bosons. And this concludes the proof of differentiability and v-representability for 1 RDMs for elevated temperature. So now I'm at the end of my talk. So a small summary. So we showed that this set N is the set of all v-representable densities, and that the universal functional is differentiable for all 1 RDMs in this set here. And then possible further work would be to generalize this work to infinite basis sets, but there we have some additional questions. For example, under which condition is the partition function finite? So the partition function is the normalization in the Gibbs state. And of course, if we sum over infinite states, then we need to know that we actually get something finite. And also that for this, the achievement for the minimum in the definition of F, we cannot just use the theorem used in the finite dimensional case, so we also need to study that. So yeah, I'm finished.